Okay, everybody, we're going to get underway. So the plan tonight is we're going to finish up ideas from chapter 3. That's the last of the chapters that we have to be responsible for the upcoming exam. So I think we're at a really good spot to be able to have brought to closure some of the ideas and then to continue to practice and improve. And I'm going to give you some suggestions tonight as far as I think the best strategies heading into the exam. I'm also going to cover a little bit of the logistics pertaining to the exam because I want you really comfortable and familiar with how that's going to go down. So tonight we're going to talk some details pertaining to the upcoming midterm exam, and we're going to be exploring this idea that's at the end of chapter 3. It's in both sections 3.6 and 3.7. When it says using quantitative information from balanced equations, that's under the heading of stoichiometry. When we looked at earlier parts of the chapter, we did math, we did calculations, but when we were calculating the empirical formula, for example, we didn't have a balanced chemical equation. In this final section, we do. So this is a really important topic that we're going to see again and again throughout the semester and into next semester as well. Now, we still have a couple people I know that are joining up with us. So I want to begin with an initial question for you all on this topic. Okay, so I know that someone within the class celebrated a birthday yesterday. That someone was me. So what I'm curious about is, how old do you think I am? You've heard my jokes, you've heard me make a few references, you might have seen me in a video or so. I want you to tell me in the chat. You'll get credit either if you say how old I was before my birthday or how old I am today. So how old do you think I am? Give me a number. This is not an easy question. Um, I'm finding fascinating what's coming in. I'm seeing some correct ones within here. Correct answer on this one. Over the weekend, I was 52. Today, I'm 53. So I saw some correct ones within this. Um, Overall, I appreciate the contributions. Uh, I wish I had a birthday cake like this. I did not. All right, I'm just like the rest of you, stuck in at home. Uh, maybe post pandemic we can get together, do some celebration. Who knows? We'll see. Uh, Moving on to then some course details. So the exam that we have coming up, the format's going to be multiple choice, but I know it also has a few where you're asked to enter a calculated value. So they're all very closed response. The machine can score all of them. So it's going to be a combination of multiple choice with a few where you calculate something and you enter the value. The coverage for the test, it's going to be the first 3 chapters, 1, 2, and 3. The format, the delivery of it, it's online. We use Carmen in order to deliver the test to everybody. It's what we did last semester, and I'm really confident it works well. There's a little bit that we can do to practice to make sure it works well, but I'm sure that the delivery is going to work for everybody. Now, when is it? So it's next Monday night, February 8th. Now, if you look on the syllabus, there's some exam details. So it mentions how it's going to be delivered through Carmen. Everybody takes it at that particular time slot. The format for it, it's a Carmen quiz that'll deliver questions to you one at a time. That's the format, how it's set up. So you can't go through all the questions and go back. I think it's a very fair setup. You see a question, you're asked to answer it. See a question, you answer it. So that's the way it's set up. Now, in order to practice that, we have some practice exams for the midterms that I'm going to talk about in just a second. I think a really good feature of those is it allows you to practice the format for what the test is going to be like. Now, you'll be taking it wherever you're taking it, wherever you're at right now, all right? So you can use whatever resources you'd want on the exam. I mean, I can't stop you from looking in your notes or something like that, but I know you need to be really strategic like that. I know that if you have too much information, you say, well, I'll always look it up. I can't always look it up. You're going to run out of time on the test. So I'm trying to prepare it so that we can make and be successful within the format for what I know you're going to have when you take the actual test. The details within that, um, as far as the test and stuff, I think that the practice tests are a really good clue for what you should expect. Now, couple details then. So first of all, if you know that particular time slot next Monday night and you have a conflict for it, what you want to do is if you look on the syllabus, you can see this link for the makeup policy for midterms. When you click on that, it'll give you information about what makes for a, if you want to say excused absence within that. And then right at the bottom there is a link for you to request a makeup exam. So if you know that you have a time conflict, maybe it's another class, maybe something else, please look at the makeup policy as soon as possible so you can put in the request so there's no penalty attached to you. Okay, so that's one suggestion for you. Now, the suggestion I just made about the makeup exam, that shows up in these important announcements. Let me send you a polling question. I'm curious about this. When it comes to these announcements, tell me what you've already done. Have you already read these? Are you aware of them, but you've not read them yet, or you're not aware of them? Where do you stand on this? So within the polling on that one, we're almost 3-1 as far as folks have already looked at this. Outstanding. Most every question that you have as far as how is the exam going to be set up, what's the timing of it like, what's my web browser like, all of those details, please look within the announcements here. Okay, please look within the announcements because they do a really good job of setting it up so you know the entire plan. To share with you a few of them, there's an announcement that says, how do you prepare your browser for the exams? So if within that one, how do you prepare the browser? If you click on that one, it tells you very specifics for what's going to work well for taking the exam, as far as what kind of browser should you be using, how do you set things up, what you should do, what you should not do. So this is going to be really crucial for you. Okay. Before we meet next time, please take a look at this announcement. It was posted on February 1st, my birthday. Please look at my birthday announcement here, and it's going to tell you how to set up your browser to be able to properly take the exam. We did this last semester, that same setup, and it worked outstanding. Okay, I had hundreds of students take it, and I only had like one student all semester who had a technical glitch. So I know it's going to work for you if you prepare ahead of time. The other one set within there where it says important information about midterm one, this has a lot of very helpful information. Uh, I got to sort of scroll through what's here. So it gives you really good information about what it suggests that you do as you prepare prior to the exam, how the exam is going to be delivered, what happens if you need SODS accommodations, and then really important at this end one right here, even if everything seems to go well for you, when it comes to actually take the exam, what would you do if you ran out of time? What if you had internet difficulty? What if you accidentally submitted it? All really crucial information, okay? So to be a good strategic student and not stress out, really look at both set of those announcements because I think that they are going to make it so you have a much better understanding of what the plan is going to be. Now, in terms of a plan, I know when our exam is going to be. Okay, so it's going to be next Monday night. I know as far as what can take place between now and then to get you prepared. Well, I've got office hours next Monday. So if you've got questions and you want to show up at that time, I'll be very happy to answer them. What would I do as far as my plan to get ready? So I've mentioned it's going to be really important for you to read the exam announcements. Those two that I just mentioned, so you know the logistics and you got a good understanding for what's going to go down. Next, we're going to look at the topic of stoichiometry in class today. I know that the mastering chemistry homework that I have coming up includes questions involving stoichiometry. And on Thursday, I think we'll have a time to review some ideas, maybe add a few in that I think are still going to be important for us. But I really like this breakdown of how we're wrapping up the content today. You're able to practice it within mastering, and we'll have a little bit of idea chance to review on Thursday. I think that's a really good setup. In recitations this week, whenever you meet, the topic is going to be stoichiometry. So I'm really confident that you're going to improve your skill with that. Now, other things that I would then think about Tuesday and Wednesday, today and tomorrow, I think it's really important to bring together your understanding of the ideas that we've already had. Consolidate your understanding by transforming the instructional material. The things that you've been hearing about, doing, summarize those, bring those ideas together. So which ideas are those? What I would do is, I would say for chapters 1, 2, and 3, I've been trying to tell you what the questions are. I've been trying to communicate what the learning objectives are. So when I say consolidate your understanding, see if you can summarize all of these. These are the learning objectives that I know are going to be on the test. And I've set these up so that they go from the easiest to the most difficult in a given chapter. This is based on what we usually see on exams. So just start at the bottom of the pyramid. Start giving yourself a summary and trying to make sense of the ideas from the bottom on up. In chapter 1, we had a few ideas. In chapter 2, we had quite a few more. A lot of things at the bottom of the pyramid that you're going to have to memorize or recognize, doing isotope calculations. Notice way at the top of the pyramid, experiments of Thomson, Rutherford, and Millikan. That's going to be at most one exam question. Okay, so master all of these things at the bottom of the pyramid. Make sure you have those skills so you can do well with those ideas on the test. Same thing with chapter 3. What ideas are going to be important? What learning objectives? They're listed right here on the right-hand side once again. Now notice way at the top of that, that was something we introduced last time, combustion analysis. At most, that's going to be one exam question for you. I know that there's a lot of different steps to that. It's involved, but start at the bottom of this. Master everything that are the easier skills to bring together. I know that if you just started at each of those sections from the bottom and worked up, you're going to be starting the exam at probably 60%. I'm not saying that that's going to be your maximum score. I'm just saying those are skills that are at the bottom of the pyramid. So start there and have that be what you transform and summarize. Now, we're going to have practice exams that are now available within Carmen. So they're in a Carmen module called, cleverly enough, practice exams. So within this one, I know that these are really valuable and helpful within your learning. You can practice the test taking format. You're going to find representative exam questions that we had on previous tests. All of these practice exams are also going to give you feedback. My colleague, Dr. Stofus, worked really hard to construct feedback for all of these, and we have 3 of them put together. So what I'd like you to do is, within the module section, this is within Carmen, go down to the heading for practice exams, and you see 3 different practice exams for you to work on. Timing-wise, what I'd suggest is try to get the first one done, the first practice exam, before we meet for class on Thursday. The practice exams are not graded, so don't worry about your score. Use it as feedback. Try to get it done before our class on Thursday, because I'm going to look at what the strengths and weaknesses are, and that will be information I use when we're going to seek to review. Then what I would do is, over Friday, Saturday, and Sunday, try a second practice exam and use the feedback to improve. And then you've got another practice exam, use the feedback to improve. When we have these, I know that students, they do improve as we go through the different practice exams. The one mistake I see is a student will say, well, I took one, I think that should be okay. Or they take it too late to improve. If you take a practice exam Monday morning, it's going to do almost nothing for you. You don't have time to use the feedback to improve. So I would say after today's class, after today and practicing within mastering, you will have had all the ideas. You're going to get better at them. Start taking the practice exams, and we can use the feedback so you can improve. That's my plan. So I said we had one more set of ideas. Now, it's a big one. It's dealing with stoichiometry. So let's dive right in and explore the ideas involving stoichiometry. So in order to do this, I first want to try to connect the topic of stoichiometry to skills that I think you already have. I have frequently said that when you have a balanced chemical equation, it's like having a recipe. So let's look at a recipe a few different ways. So let's say this was a recipe for making a drink. 6 ice cubes plus 1 can of soda gave you 2 drinks. So without any fancy math involved, let's say you had 6 ice cubes and 2 cans of soda. And if you're following the recipe, let me send you a polling question on this. How many drinks could you make here? Given that recipe and those amounts, how many drinks? Take about 10 more seconds. Okay, so our consensus on this one is you can make 2 drinks out of it. So let's see if I agree with that. So I got my cup right there. I put in 6 ice cubes. I pour in 1 can of soda. Yep, it can make 2 drinks. I've got an extra can of soda left over, but I agree with you all. I think by looking at the amounts and how they combined within the recipe and how much I started with, I agree with you. Let me send you another one, another polling. This is a different one that we're going to try to use, a different recipe. So within this one, we've got a recipe for a sandwich, 2 slices of bread and 3 pickles. That will give you 1 sandwich. So let's say you had 4 slices of bread and 9 pickles in your cabinet there. Take a second, think about that. How many sandwiches could you make? So as this one is coming in, I think you are excellent sandwich makers. I'm seeing almost 100% agreement on this. Take about 10 more seconds. Almost everybody within this one says you can make 2 sandwiches. I agree. You've doubled the amount of bread. You've um, you've got 3 times as many pickles. So you could definitely make it though, because you have 4 slices of bread and it's 2 per sandwich. I agree. You can make 2 sandwiches within the whole set. Well done. I think we're better. We're strong sandwich makers within our setup here. Let me ask you this one. Okay, I've got a couple more. I'm curious. So within the sandwich one, we had a really strong result, almost 100%. I'm curious within this recipe. This one is, again, back to making our drinks. We've got a recipe that involves ice, soda, and how many drinks we can make. We've got a certain amount of ice cubes and a certain number of cans of soda. What are you going to run out of first? Take about 5 more seconds. With this one, I'm seeing another really strong consensus, and I'm going to agree with you. I think you're interpreting the recipe correctly. That you could see that you've tripled the number of cans of soda, but you didn't triple the number of ice cubes that you have. So you can look between those two, and proportionally, you're going to run out of the ice first. You've tripled the cans of soda, but you didn't triple the ice cubes. So if you were at a party here, you would be running out of the ice first. Now, this next one, I'm going to transition this one a little bit differently. So here we see a recipe and a chemical formula. I would say the formula is like the recipe. We have coefficients once again, and those are telling us the amounts, often expressed in moles, for how the things are combining. So in this case, I want you to look both at the recipe and at the chemical formula there and select all that are true. So I've got a combination of questions on this. Which of the relationships are correct? We've seen a really strong consensus once again coming in with this. Take about 10 more seconds. So within this one, I agree with the crowd here. 95% of the class is choosing B as being correct. I think that's the only correct statement there. I think that's correctly looking at the coefficients. And in a way, what you've just done right there, you've solved 3 stoichiometry problems within this. You were looking at 3 different stoichiometry sets of relationships where you had a recipe and you were comparing the different amounts to see how they fit together. I got one more within the set, this one. So this is another combination. There's both a recipe and there's a chemical equation. It's another scenario where I'd like you to select all of them that are true. It's discussing aspects of sandwiches and aspects of the chemical equation. Take about 10 more seconds. And once again, we're really close to 100% being correct within that. I think only B was the correct relationship there. My point within this one is I think you are really capable of interpreting the coefficients. You were really doing a great job when we were looking at recipes. And I think you're doing a pretty good job when we were looking at chemical equations. Uh, One thought for me. I don't know what you think about this. In the chat, tell me, do you think it's any more difficult when you're trying to make sense of the coefficients when you have a chemical formula compared with a recipe? We had a combination of those. Some were recipes, some were the chemical equations. What are your thoughts about interpreting the coefficients there? Is it more difficult with the chemistry part? What do you think? Tell me why. The main feature I see coming in when you're doing, as you make a comparison, if you say there is a difference, is trying to figure out aspects of the subscripts. If something like that might be making it different. I think that's an insightful comment because that's about the only feature that I see different within here. It's about the only feature that I see because for each of these, I've got a number that goes in front, and then I have something that it's describing. It might be slices of bread. It might be H2 molecules. So I think within here, as we move on and we look at the other aspects of this stoichiometry, the reason I show different recipes and ask you to look at those proportions, man, you were doing an outstanding job. In almost all of those, within 10 seconds, 20 seconds, you sized up the situation and you were not intimidated by the math. You didn't need some very elaborate plan. You were making sense of the information. Let's keep that same skill when we now consider these chemical examples. I know you can do it. Okay, you were doing a really good job looking at the relationships, and the coefficients are telling us the proportions. It might be in our recipe for sandwiches. It might be in our chemical equation. Keep that skill because I know you got it. You just demonstrated it. When we have within here our chemical reaction, we could be thinking of it in terms of the molecules that are involved. But notice that the coefficients in front, those are telling me how those parts combine. The coefficients are telling me how the molecules can react with other molecules. Or it could be moles of the molecules reacting with both. So those coefficients we're going to see correspond to either the actual number of molecules, or if we've scaled it up, the mole amounts. And I know you can handle that. You just did a great job looking at with proportions like that. Just one feature I want to bring up with this. I think that it would be fine if I said I had 1.75 moles of H2 reacting with 0.65 moles of O2. I could imagine a reaction like that. The second one, 1.75 molecules with 0.65 molecules, I'm a little confused by that. I don't think I can have a fractional of a molecule. I can have a fraction of a mole amount, but I can't have a fraction of a molecule. If you tell me I have 1.75 moles of H2, that's no big deal. I'll multiply that by Avogadro's number to see how many molecules I have. So my point is, a lot of times students say, well, can I use the coefficients for either molecules or mole amounts? Absolutely. The only point I'll raise is within that setup, you can't have 1.75 molecules, but you could definitely have 1.75 moles. That's the only distinction I want to bring up for you. And it's not a big one. So now when we look at these, how they combine, they're going to combine telling me how moles combine with moles, the coefficients will, or the number of molecules with number of molecules. But it's not grams combining with grams. The total mass before and after is the same, but we combine based on the particles themselves, not their masses. So when we're looking then to use the information involved with stoichiometry, our first step needs to be to convert from grams to moles. And when we're finished, we might convert from moles to grams. But when we're using the coefficients, moles combined with moles, or number of molecules combined with number of molecules. This idea of using the balance coefficients and seeing how moles combine with moles, that's true for any part of stoichiometry. If you're using dimensional analysis, you can follow that scheme that I have outlined right here. If you're using a BCA table, you're also following that scheme. Both of them are the same. They just are set up differently in terms of their accounting within their bookkeeping. You're not required to use a particular approach. I'm going to try to point out a few reasons in tonight's talk where I find a BCA table to be useful, but I'm going to work through several examples where I show how it can be solved using one approach or the other. I want you to have an approach that you can master and be successful with. At the core, they're doing the same thing. They're converting from grams to moles, figuring out how moles react with other moles, and then perhaps taking that and converting it back to grams. Let me work through a couple examples here. And as I work through these, I think based on the pre-class video, you're probably already trending a little bit to say, I'm a dimensional analysis person. Or maybe you're trending and saying, I'm a BCA table person. That's fine. As I step through these, when I discuss the one that's more central to what you're thinking about, really pay extra attention to that one. So this one, first of all, how many moles of H2 are required to completely react with a certain number of grams of N2? When I'm doing stoichiometry, I need a balanced chemical equation. Here's my balanced chemical equation. In front of N2, even though it doesn't show it there, it would be a coefficient of 1. So if I look at this based on dimensional analysis, I'm going right through the steps that are shown right here. I'm going to convert from grams to moles by using the molar mass. When I look at the periodic table, nitrogen has a mass of 14, and I'm looking at an N2 molecule, so it has a molar mass of 28 grams per mole. I'm then looking to see how they combine in the balanced chemical equation, and I'll use that to determine the number of moles that I have in the product. This step right here of using the coefficients, that's similar to what you were doing just a moment ago when you were making sandwiches. You were looking at the coefficients on that. The coefficients are describing a ratio. It's a proportion for how one reactant combines with another. For every 3 moles of H2, it takes 1 mole of N2. That's what the coefficients are telling me. How about this example right here? How many grams of NH3 are produced when 28 moles of N2 react? I need a balanced chemical equation. That's exactly what I have. In this case, I already have the moles. I did not need to convert from grams to moles to get started. I already had the moles of a reactant. Now I'm going to look at the balanced chemical equation and consider the coefficients. I see that I have 2 moles of NH3 for every 1 mole of N2. That's what my recipe is telling me. We want, in this case, at the end to report it in terms of how many grams. So I looked at the periodic table and I add up the mass for NH3. I see that nitrogen is 14 and hydrogen is 1. 14 plus 1 plus 1 plus 1, that gets me to 17 grams per mole. And that would be my answer here. This would be set up using this exact scheme that I see here at the top. Now, if I were doing the same thing with the BCA table, it should lead me to the same answer, and it will. So within this case, in the table, when I'm looking at this, what I have before, how does it change, and what do I end up afterwards? What I'm going to put in my table are going to be the mole amounts or the actual number of molecules, because we just said moles react with moles. So within here, I had 28 moles of N2 to begin with. I'm going to use them all up. So in the change line, if I started with 28 moles, that goes down by 28. I'm using up all the N2, and I'm asking the question, how much NH3 could I form from that? In this case, I'm going to look at a simple proportion. This is exactly what you were doing when we were making sandwiches and drinks. I see that for every 1 mole of N2, it gives me 2 moles of NH3. I've got 28 moles of N2. How many moles of NH3 would it give me? I'm just going to set up and cross multiply and divide and find that it gives me 56 moles of the product. It goes up by 56. I started with no product. It went up by 56, and afterwards I've got 56 moles of it. Now the 2 examples that I just gave right here, they're both the same. They're both looking at the coefficients and following the recipe. Within this one, if I wanted to know how many grams was involved, I would come out of the table by using the molar mass. So when I have values that are going into or out of the table, when I'm looking at BCA values, I will be using the molar mass And then once it's in the table, then I'm using the mole amounts with the coefficients. Now, for some of these, let me step through and see a few different ways that we can ask this. A few different ways that we can see applications of stoichiometry. So within this one, we are given a description. We have a scenario for what's involved. It's taking place in a sealed container, and we want to know what remains afterwards. Here's the balanced equation. Hydrogen gas reacts with oxygen gas to form the H2O. When it says hydrogen gas, I'm thinking the H2 molecules. When it says oxygen gas, I'm thinking the O2 molecules. If I track through that within a BCA table, what information is it telling me at the start? It tells me that I have 10 moles of H2, 7 moles of O2, and I don't have any of the product there. The H2 gets used up. It goes all the way down to 0. I started with 10. I use up 10. Goes all the way down to 0. When I look at that, when it says the hydrogen gas is consumed, that's what it's saying. All of the hydrogen gas is being used up. Now, how do I get the other values in the change line? In order to get the other values in the change line, I can use the coefficients. The coefficients will always be telling me what's going on in the change line, and I can just set up simple proportions for that. It tells me that for every 2 moles of H2, I have to use 1 mole of O2. I've got 10, so I have to use up 5 of the O2. This is just looking at the coefficients and keeping track of them, just like we did with our recipe before. The coefficients tell me that 2 H2 react with every 1 O2. So if I have 10 H2, I would need 5 of the O2. When I'm looking at the amount of H2O that forms, I think it's even easier. Coefficient of 2, coefficient of 2, it's the same coefficient. So if I use up 10 of these, I'm going to get 10 of the H2O. Now, last thought within here, all of the values in the change line have to be consistent with each other because all of the coefficients are consistent with each other. So my point is, if you instead ask the question, I wonder about the relationship between O2 and H2O, does that give me the same answer? It will. All of the values within the change line are consistent with all of the coefficients. In fact, some of the high school teachers I work with, instead of calling it the change line, they call it the coefficient line. That's what they say C stands for. Look at the coefficients. 2, 1, and 2 are in the same proportions we see as 10, 5, and 10. They're just getting scaled differently. They have to because that's what the coefficients are telling me. And then if I were to see what do I end up with, I had a certain amount before, it changes, and I see what I'm left with at the end. A certain amount before, I see how it changes, and that's what I have when I'm left with at the end. So this is me tracking one through where I had a limiting reactant. I finished up the H2, it went all the way down to 0, and I had some of the excess reactant, the O2 left over. Now, I mentioned that we could do this also with actual molecules. Here was one that we did a couple classes ago where we were looking at different reactions involving aspects of combustion. And this was a particle level picture. This was given in terms of the number of molecules. Now, let me give you a strategy here that's going to be appropriate if you're a BCA table person. And I like this feature right here. If you're a BCA table person and you're trying to say, well, what is the limiting reactant? All you have to do is just pick one of the reactants and check it. Just pick one of them and check it and see if that's feasible. Let me show you what I mean. So I've got 2 possible limiting reactants. It's either the methanol or the O2. I'm just going to pick this first column. I'm going to say that I started with 6 molecules and I use up all 6 and it takes me down to 0. I just picked that column. Now I'm going to check if it works. The coefficients tell me that for every 2 molecules of methanol, it takes 3 molecules of O2. 2 molecules of methanol go with 3 molecules of O2. So if I have 6 molecules of methanol, I would need 9 to keep the proportion the same. I'm going to consider that. Can this go down by 9? No, I only started with 6. I've chosen the wrong column. No big deal. Right there, that tells me, hey, dummy, use the other one. Use up all 6 of the O2 and take that down to 0. Now it's going to work. Now that I'm going to see that the coefficients of 2 goes with 3 is the same as 4 goes with 6, I can put those within my line. I see that I use up all of the O2. I have methanol left over. If I look to see how it matches up with the coefficients, I would make 4 of the carbon dioxide, 8 of the water, and that tells me what I end up with. One of the features that I like when I'm using a BCA table, it's really easy to figure out what the limiting reactant is, because you just try one of them in the column. You try one of them and you see, does it go down to 0 and leave some of the other one left over, or does it use up more than you started with? You can't use up more than you started with. So that's how I like the BCA table as a useful check for me. Now, let me show you within this one how this goes down if you want to consider a limiting reactant using dimensional analysis. So here we have a balanced chemical equation. I got this balanced chemical equation from this word description. So let's practice the word description. Magnesium metal reacts with oxygen gas to produce magnesium oxide. Magnesium metal is talking about magnesium solid, the elemental form. Oxygen gas is talking about O2. Magnesium oxide, ionic compound. Magnesium is in the +2 column. It's an alkaline earth. Oxygen becomes oxide, which is in the -2 column, so it must be MgO. And then I'm going to balance it from there. So if I'm using this with dimensional analysis, I'm going to try one of the reactants and figure out how much product that I can make. So if I start with 56 grams of magnesium solid, I look on the periodic table and 1 mole is 24.3 grams. So I'd be starting with 2.3 moles of magnesium. I'm going to use the coefficients now and see that I form 2 moles of product for every 2 moles of that reactant. So by going through my dimensional analysis, and it's the same of what I have up there at the top, I find that I could form 2.30 moles of magnesium oxide. That's based on the amount of magnesium there. If I do the same thing with the other reactant, I consider how much of the O2 I'm starting with, 64 grams. I convert that to moles. I use its coefficients. I see that I get 2 moles of product for every 1 mole of O2. That tells me that I could form 4 moles of magnesium oxide. Now, only one of these can be correct. The one that is correct is the one that gives me the smaller amount of product. Because once I run out, I'm done. It's just like when we were making sandwiches or drinks. Once we run out of one of the ingredients, we can't keep making things. That's what the limiting reactant is. So I think within this one, when I'm looking at the different details, how much product is formed, I would form 2.30 moles of the magnesium oxide. The magnesium solid is the limiting reactant, and the O2 is something that I have left over, the excess reactant. How much of the O2 was used up? Well, I could go back and find out within this one. I formed 2.30 moles of magnesium. By using the coefficients, I could figure out how much of the O2 was consumed, and I can compare that with how much I started with. This would be my approach if I was using dimensional analysis to solve this problem. However, if I had my choice, I probably would not use dimensional analysis. Anytime that I'm asked more than one detail here, what is the excess reactant? How much of it's left? How much product's formed? As soon as you ask me more than one aspect of the problem, I'm going to want to summarize it in a BCA table instead. Because personally, I like seeing all the answers right there in front of me, and they'll all be present within a BCA table. So within the same setup right here, I'm going to convert in each of these cases to figure out how many moles I have of the magnesium and the O2. So I'm using the molar mass of each of those to put mole amounts within my BCA table. One of these is going to be the limiting reactant. Let me just pick one. So I'm going to say, what happens if I use up both moles of O2? I would need to use 4 moles of magnesium. I can't use 4 moles of magnesium. I only started with 2.3. No worries. I'm going to switch over and say, no, the magnesium is the limiting one. Now I can simply look at the coefficients that I have and figure out the change line. I can combine that now to come up with what do I end up afterwards. When I say that I like seeing all of the answers at the same time, I see all of the answers right here all at the same time. So at least with me, as far as the clarity of what was involved, I think that a BCA table, again, for me, it works better when I have multiple things that I need to report. And this one quite clearly tells me that I ran out of magnesium, O2 was in excess, I've got 0.85 moles of it remaining, and I formed 2.30 moles of the magnesium oxide. Now, both of these are equivalent. Both of them equivalent in that you can use both of these techniques to come up with the right answer. Now, I know within perusal, I sort of asked, well, what's your opinion on one of these? Which one do you think's better? And so I found it was really insightful, the comments that you were sharing along the way. This is something I've studied a little bit. And what I found is if you already feel very comfortable with dimensional analysis, if you feel like that's something that you know how to use and you can solve problems that way, I don't want to talk you out of it. You can always use dimensional analysis. That's completely fine. But if you're coming to this and you're sort of learning about stoichiometry or relearning it, and you're not a pro yet, I found that the BCA table in general works a little bit better. And the reason it works a little bit better is because the amounts are clearly connected to the balanced equation. You see the balanced equation right there. It's staring you in the face. And so you can clearly see how the different values are related to that balanced chemical equation. You can see all of the relationships that are taking place at the same time. I find with dimensional analysis, in some ways, you've got to be even more conceptually astute because you need to be able to see from these numbers all of the different relationships. In a BCA table, the relationships are just shown right there in table form. They both work, but again, if I have to report more than one thing, I like the BCA table. Now, here's another example where you could do it, again, with either approach, but in this case right here, I think this really is benefits from using a BCA table. So in this one, we've got the same reaction as before, and we're adding some hydrogen gas. We're adding, 12 moles of hydrogen gas and some O2. It doesn't tell me how much, but it tells me how much of the product is formed. And it also tells me I've got some H2 remaining. So this is where I would start. I know how many moles of H2 I began with. After the reaction is complete, I have 8 moles of H2O. I also have some H2O left, some H2 remaining. And that must be because the O2 went all the way down to 0. Now, a key thing within here, I think I have enough information to fill in the rest of the table. That seemed like an odd assortment of information about what you started with, what do you finish with. But a crucial thing here is when it comes to that product, I started with 0 there. I finished with 8, so it must have gone up by 8. I have gotten it to a value on the change line by looking at the products. I started with 0, I finished with 8, so it must have gone up by 8. Now I'm in business because soon as I have one value in the change line, I can look to the coefficients and I can get the other values. 8 to 4 to 8 is the same as 2 to 1 to 2. You could set up proportions for all of those, but I'm using one value on the change line to get to the other values. And then I can just fill in the rest of the table from there. If I have a scenario like this, I'm definitely going to favor using a BCA table. I noticed within perusal, several folks had questions. Well, if you were doing dimensional analysis, how would you go about this? That's a tougher one for me to explain. I think you could do it. You would once again have to start with information about the H2 and begin to work it backwards. But for clarity within this one, I find using a BCA table really beneficial. Now, I've brought up a couple different kinds of stoichiometry problems. And I've also brought up a couple different ways that we can solve it. When I'm looking at all of the ideas here within chapter 3, I also have insights for the ones that are involving stoichiometry. When I'm putting them in this big box right here, I'm also putting them where the ones at the bottom students score higher on, and the ones at the top are more difficult. So let me give you details on this. So just like I'm saying, start at the bottom of the pyramid and work your way up. We can do with the same thing with stoichiometry. This is something I've researched because I'm curious what made questions more difficult, and this is what I found out. So first of all, at the bottom here, so many times it's stoichiometry problems, you have to have a balanced chemical equation, and it might involve converting from grams to moles or from moles to grams. We have found that those bottom skills you are going to be really good at. You're going to be very proficient and capable of writing balanced equations and converting back and forth from grams to moles. So we have found that when we look at your results, it doesn't matter. You can do both of those skills, and I know that you're going to be able to. So that is not really something that makes a question more or less difficult, because everyone has those skills and they're able to accomplish it. Now, the easiest question type within that box is looking at one where we ask how much product forms. This one at the top here, this is an example. This is one that we looked at earlier tonight. How much product is going to be produced given a certain amount of a reactant? That's the highest scoring stoichiometry question we have. You've got information we're asking about, well, tell me how much product forms. More difficult is when there is a limiting reactant. Here's an example from the e-text on that. Because after all, when you have a limiting reactant, if you're doing dimensional analysis, you need to check both pathways. You've got to figure out which of the one leads to the least amount of product forming, and that's corresponding to the limiting reactant. Or you can track it through within a BCA table. A limiting reactant problem scores lower than just asking about the product. More difficult is one where the question is not simply what is the limiting reactant, but we ask, well, how much of the excess one is left over? That sample exercise that you see right here is an example. There's a description of the reaction and it says, what is the excess reactant and how many moles of it remain? Or this practice exercise 2, it steps you through different ones. How many moles of the excess reactant remain? I showed an example of that earlier. That was the one involving the magnesium and the O2. Both of these, this is an example where I see students have better success with the BCA table because the answer is right there in the table. So when I'm trying to do comparisons as far as what strategies appear better, this is one where many times a BCA table I see students having better success with. You don't have to turn in your work. You don't have to show me what you're doing. But when I've studied it, I can understand why this question about how much of the excess reactant remains, it ends up easier with the BCA table. Now, at the top right here, one of the most difficult ones is ones where I'm saying it involves reactants and products, and it's very specific to a BCA table. That was at this example right here, where we have a scenario with different amounts given. And when it comes to working the BCA table, you might have to sort of work it backwards. You might have to look at different relationships that are within that. That's one of the more difficult ones involving the stoichiometry because I think it requires the most skill with a BCA table. It's really not that different. I mean, you're still working on columns, you're still looking at the change line, but I can understand why that would be one because it's not as easily solved with dimensional analysis. Now, we've got two more types within the box that I want to bring up here. One of them is stoichiometry involving particle representations. We looked at particle representations earlier in the chapter when we looked to see, first of all, how do we make sense of a chemical equation? And we looked at how we had these particle representations describing what was going on. This would be an example. So we have a balanced chemical formula at the top. We're combining N2 and H2. And the question is, okay, at the particle level, what does that now look like? This is adding N2 and H2 to a sealed container. That's what this box is representing. What I'd like you to do is see if you can make a sketch of that. What's it going to look like in the box after the reaction goes to completion? Give that a try. Let me show you here how this is consistent with what we've been looking at involving stoichiometry. So first of all, I see that the product formed is going to be NH3. That's the molecule there. So I might make a sketch of this being what NH3 could look like. I want to have it where it has a nitrogen atom. Those were the larger black ones, and 3 of the hydrogens around it. We're going to look a lot more later in the course as far as how we draw those and what the geometry looks like. But at this point, I think that's a pretty good representation for nitrogen with 3 hydrogens present. Now, if I want to keep track of the different parts, I could use a BCA table for this. Because this is, after all, a balanced chemical equation, and I can use this with the molecules combining with other molecules. So if I were to take my table right here and plug in what I have before, I see 2 N2 molecules. I see a total of 7 H2, and I don't see any NH3 present. Now, let's use this right here as an opportunity to look at what those subscripts mean. When we were looking and we were comparing recipes with chemical equations, people said sometimes the subscripts are what mess you up. Notice what the subscripts are telling me. The subscripts are telling me that this involves N2 molecules. The subscript 2, it's saying I've got 2 of those molecules together. Or I've got H2 molecules. Subscript 2 is telling me I've got 2 hydrogen atoms within that molecule. Or NH3 is telling me I've got 3 hydrogens present. Those subscripts right there, they're not involved at all as far as coefficients. They're just telling me the parts that are there. Now, if I were to take this then and track this through just with my BCA table, let me try the first column. If I use up all of the N2, 1 goes with 3, so 2 goes with 6. Okay, that works. I haven't used up more than I started. I could then see that I would form 4 NH3 there. So then I'd say, what should be in the container when I'm done? All of the N2 is used up. I've got 1 H2 molecule remaining, and I form 4 NH3s. Using this would give me an image like this. I see that I have an H2 molecule as excess, and 4 NH3 molecules are being produced. So sure enough, this is consistent with what the BCA table would be telling me. Now, when I look at this one and I ask, well, what makes this more difficult for students? This is one of the more difficult stoichiometry problems. These are the key details that I need you to look for. You want to make sure that you have the correct molecules present. The molecules that were possible in this would have been N2 molecule, H2 molecule, and NH3. That's why I identified right at the start, that's what an NH3 molecule could look like. One mistake that I've seen on this is students get really strange combinations for what they think could be afterwards. We need to have the correct molecules. The correct molecules were possibly N2, H2, and H3. We need to account for a limiting reactant if that was present, and we need to include any excess reactant in our final picture. This is what I've seen as far as what makes it a more difficult problem. Will you have one like this on your exam? Excellent possibility. Okay, I've seen this one many times, and by this one I mean a particle representation where you need to identify what's in the container afterwards, and keeping track of it with a BCA table doesn't hurt. The other category that we have within here are questions involving stoichiometry and what's called yield. Let me introduce that for the last set of ideas within this. And then I think we're in really good shape to at least have a first introduction to the ideas that we have involving stoichiometry. Let me show you where yield fits with respect to these other ones. So here's a reaction stoichiometry problem. 60 grams of aluminum reacts with 96 grams of O2 to produce Al2O3. And we have a balanced chemical equation. It says calculate the theoretical yield in grams. Theoretical yield means apply the stoichiometry just like we've been discussing tonight. And in theory, how much should you get? So everything that we've been looking at tonight so far involving stoichiometry is all in the category of what is the theoretical amount? That's what we've been working at. So what I'd like you to do is give this one a try right here. You can use either dimensional analysis or you can use a BCA table. I'm going to show both of them work through so you can check your work. See if you can set this up. Grab a calculating device. I'll give you a couple minutes on this. Try to give this a try. You've got a balanced chemical equation, a certain gram, 60 grams of aluminum, 96 grams of O2. Try to set it up, and then I'll share my work. Take about 2 more minutes. You might not finish all of it, but at least try to get your thoughts together, please. So here's my thought as we work this one through. So here would be an approach where I'm stepping through using dimensional analysis, and I'm following the exact procedure that was described earlier within our outline. We're going to go from grams to moles. We're going to use the coefficients, and then we'll figure out how many grams of product I could form. And if I do the exact same thing with the other reactant, I'll figure out the amount of product I could form in each case, and I'm going to be choosing the one where I form the smaller amount. This would be calculating the theoretical yield. In theory, if I apply the coefficients, this would be the amount of product that I could form. Now, if I'm using a BCA table, and Personally, I probably would use a BCA table. I've been converted to these. So I show the mole amounts using the molar masses for what I initially have. I'm going to figure out the change line that's consistent with that. I'm going to choose and say, well, what if I use up all of the aluminum? I see that, oh, I've got some O2 remaining. So that would be the correct choice. And I could use this to figure out what do I end up with in afterwards. This would be my setup if I was using this with a BCA table. This gets me to the same theoretical yield. Now, I want to add to this a different way of thinking about yield. When we talk about the yield of the reaction, the theoretical yield, that's based on the stoichiometry. That's what we've been working with, where we have a balanced equation, we're using the coefficients, we use the different amounts. All of that is calculating, in theory, how much should we be able to get? The actual yield, that's what you actually would record in the lab, what your experiment actually produces. When you turn that into a percentage, by multiplying it by 100, that's the percent yield. So I want you familiar with all three of these terms, the actual yield, the theoretical, and how those combine to turn into a percent yield that you obtain. Now, sometimes students ask, well, can you have that be more than 100%? Have I ever seen a percent yield more than 100%? In truth, all of the time, okay? This is a very common scenario. A lot of times the chemicals that we use, they really absorb moisture from the air. They're called hygroscopic. You just set it out and you can just, if you're sitting on a balance, it just keeps getting heavier and heavier because it's absorbing air, water from the air. So if you were to do this experiment and you measure the product, you're not just measuring the product, you're measuring the product and this moisture that's been attached to it. So the actual yield ends up being more than you would have predicted. There's different ways you can get around this in the lab. You could do it so you run it under very dry conditions. Maybe you dry the sample, but notice the actual, that's what you obtained in the experiment. You're not going to magically create something, but based on the experiment in itself, it could exceed what the theoretical value is. And this is the most common example why. Because other things, other substances are being something that you weigh as well. Now, when I'm analyzing questions like this, I always begin by using the stoichiometry to calculate the theoretical yield. Then, many times you're going to have 2 out of 3, meaning you've calculated the theoretical yield. The question might ask you to combine that with the actual to get a percent, or you've calculated the theoretical yield, it gives you the percent, and now you consider the actual. Here's a very typical scenario. So we've got a certain amount of N2 and a certain amount of H2. It tells me the amount of product that was formed, and it asks the percent yield. This is involving the percent yield. So the first thing I'm going to do, I'm going to calculate the theoretical value. So here I work it through using dimensional analysis. I would choose the smaller amount. Okay, in theory, I could make 45.33 grams. I actually produced 37 grams. 45.33 is the theoretical amount. 37.0 is the actual amount. So the percent yield in this case was 82%. Back to my strategy. I'm first going to use the theoretical, I'm first going to calculate the theoretical yield based on the stoichiometry. That was this value of 45. After I have that, now I'll begin to incorporate information and determine the percent yield. I don't need to rush it, okay? This would be the same case if instead it told me the actual amount and asked the percent, or it told me the percent and it asked what would be the actual there. In all of the cases, find the theoretical amount first. Find the theoretical amount first, and then consider what your missing term would be. Now, let me show you one other way, and I think this is the trickiest way that I've seen it. Consider this one. A reaction is known to have a percent yield of 50%. Based on the reaction stoichiometry, 5 grams of O2 would lead to 8.2 grams of product. There's other reactants there. This reaction right here has a yield of 50%. So if you wanted to obtain 8.2 grams, how much oxygen gas should you use? Let me send that one to you as a polling question. I'm curious what you think. Based on the stoichiometry, if you start with 5 grams, it would give you 8.2. However, it says the yield is only 50%. Take about 30 more seconds here. I know this one requires a little bit more thought. So as the last poll responses come in with that, let's look a little bit more closely again at what this question is. So this one, it says a reaction is known to have a percent yield of 50%. That's not unusual. A lot of chemical reactions have been studied many, many times under different conditions, and they know if we have certain temperature, certain pressure, how much product can we actually produce. So this idea of knowing what the percent yield is ahead of time, that's not very unusual. Now it gives us specifics about the reaction. Based on the reaction stoichiometry, when I read based on the reaction stoichiometry, I'm thinking, okay, based on the theoretical amounts, 5 grams of O2 would give me 8.2 grams of product. So in a way, they're already giving me what the theoretical description is. Now it says, okay, if you wanted to actually obtain 8.2, how much should you use? Well, if we used 5 grams, we wouldn't get 8.2 because the yield is only 50%. We're using half as much as we need. I agree with the folks that said, no, you've got to scale it up. You've got to go all the way to 10 grams because the yield is only 50%. Excellent job within your analysis there. So we're a little bit, our own yield here is a little bit over 50% nailing that particular idea. That's something I'll probably bring up again at our review on Thursday, because I know this is a little sort of a subtler way or a little bit more confusing way perhaps to think about the yield. Now, as far as where this the skill here of working on stoichiometry is, um, I list here some examples within the e-text. I've stepped through when it came to stoichiometry within my box. I had about 6 different examples, right? I had ones where we're just looking at the product, limiting reactant, involving yield, looking at the excess that remains, one suitable for like a BCA table, example with particle representations. Almost all of these, if you look within chapter 3 within the e-text, there's a really great set of resources. Time and again, what you're going to find are sample exercises. Sometimes there's video explanations. They're paired with questions that you can then try right in the spot, either if they're these self-review ones or different practice exercises. Notice the titles within here. Calculating the amounts of reactants and products where it's giving you a word description. Here's one involving a limiting reactant. So you know I oftentimes try to give you suggested problems to begin to apply and work on a given skill. The best resource I have for stoichiometry is within the e-text itself. You can look at the end of chapter and find many examples there as well, but I would begin by looking within the e-text itself. Try to work through and use your best metacognition when it comes to the sample exercises. Try to learn from those. Try to extend your understanding with the different practice exercises. And I think you're in great shape. So if we double back then to what my suggested plan is, let's focus right now on summarizing the information for chapters 1, 2, and 3, applying your understanding in the upcoming Mastering Chemistry homework assignment, which deals with calculations from chapter 3. And please try giving the first practice exam a go. We'll learn from that. I'll learn from that. And then in our class on Thursday, we'll just build from there as we try to bring in our last bit of skills that we need to master heading into the test. Excellent job, folks. I really like your attention once again tonight. Your participation was great. I'll hang around if you got questions. Let's keep it moving.
Dr. Clark, I'm wondering if you have a chemical equation and it's representing molecules and not moles, and then in like the starting box or whatever, the number of molecules of each reactant is in such a way that in the final box or the after box, there's excess of both reactants. Does that mean there's no limiting reactant, or is there still?
I agree with you that when we're looking at these, when we have, it sort of comes back to my first idea about how when you have coefficients and fractions and stuff, you can definitely have that when you're looking at mole amounts, but you could have something where you're looking at the particle level where you end up having a few stray molecules of both, but you don't have sufficient molecules to make them actually combine based on the actual reaction. I think that's what you're describing. Yeah, I see no problem with that.
But is there, would you say both of them are limiting reactants or neither of them, or what?
Well, I mean, the idea when we have limiting and excess, there's nothing wrong if you had both of them run out at exactly the same time. Maybe they're perfectly matched. And what you're describing would be a scenario where both of them run out, you can't combine them anymore, but you just might have one or two, remaining, but it can't still combine anymore. In either of those cases, I think that the language of excess and limiting, it's a little bit forced, I think that we have a picture for what's going on, but I mean, if they both go down to zero at exactly the same point, are they both limiting, or are they both excess, or does it not really matter? I think it doesn't really matter.
Okay. So you don't think that kind of situation would be, like, we would be tested on that?
No, I think that could occur, but I don't think that would be a good learning objective to try to have you answer that.
Okay. Thank you.
I was just wondering, could you explain again why you have to choose the smallest amount for the theoretical yield?
For the, when you're trying to figure out the, with a limiting reactant?
Yeah, the example you did was like, with the 60 grams of aluminum.
Yep. So, well, let me give you the opposite. Let's say that you ran out of one of the parts and you had the other one still left over, and you wanted to keep making things using that excess amount. It'd be great if you could, but you've already run out of one of the components. It's like if you're making your sandwich and you have ham and bread. Once you run out of ham, doesn't matter how much bread you still have, you are done making sandwiches. So that's what's taking place with the within anyone's, like here. Once you run out of one of the components, you got to stop making the product. And running out of one of the components means that you're making the smaller amount. Does that make sense?
Yeah, that makes sense. And then like the example you're on now for the percent yield, we can't calculate that unless we know, like, we're given what was produced by the reaction, correct?
Yep. You'll almost always have to calculate the theoretical part, but then you're right. You need at least one of the other details, right? You need to either have them give you information about what was actually there, or you need to they give you information about the percent yield, because it's actual, after all, it's 2 out of 3 things, right? It's 2 out of 3 things where it's actual, theoretical, and percent. You can use the stoichiometry to get the theoretical, but they got to give you one of the other 2 parts.
Okay, that makes sense. Thank you.
You got it.
If we're looking at actual versus theoretical yield and calculating the percent yield, does it matter whether we're in grams or moles? Or
It does not a bit.
Okay.
I have a question about the slide that you're on right now. So in the other problems, I could like understand what limiting reactant is. It's the one, it's the compound in the equation on the reactant side that's going to be completely used up, right?
Yep.
But in this example, it looks like what I would call the limiting reactant is also a theoretical yield. And so I'm starting to get confused with this example, what the difference is between the product, the theoretical yield, and the limiting reactant with this example.
The language theoretical yield, all that means is apply all of the stuff that we've been thinking about in terms of stoichiometry, and just apply that completely. And when I say apply that completely, okay, the limiting reactant goes down to 0. All of the product ends up getting formed. You don't worry about, was there also moisture there? All of this stuff of using the math that's provided and using the coefficients and the amounts, all of those skills, that tells you in theory how much you should be able to get. So when you say that you had a good understanding of, okay, how do I make sense of limiting or excess? All of that's great. All of that was thinking about it in theory, how should it work? So you were thinking about all of the stoichiometry, all of those terms, and that was describing the theoretical yield. It was telling you how the parts were supposed to combine.
Okay, so if we're thinking about the law of conservation of mass, is theoretical yield basically saying, like in this example, 2NH3 is going to be everything that 3 hydrogen and 1 nitrogen is? So like hypothetically, 3 hydrogen and 1 nitrogen would be not 0, and that's not kind of what I want to say, but like 2NH3, the theoretical yield is showing that like everything was used up and like now the product has like everything. Does that make any sense?
Yeah, you could think about it as saying that this, which I think you're saying, that this reaction right here, how it shows how things get combined, this is completely the only story I need to worry about. It's completely describing how the reactants lead to just this product.
Okay.
Yeah. Because in the real world, what would happen is, oh, well, maybe I make a different product too. Maybe I make NH4. Maybe I make a small amount of something else. You know, goofy things then begin to happen. But your understanding of, hey, the equation that you told me, that's all I need to worry about. That's what the theoretical yield tells you.
Okay. Thank you.